Hi everyone, Behzad Samadi is here from the research group. This is our first webinar on model predictive control or MPC. I will explain the basic theory of MPC and then we will see an example which is already on our application center. Don't be scared by the title. Real-time code generation and nonlinear model predictive are not usually the first things you learn about MPC. But I have organized the content of this presentation such that you don't need much prerequisite knowledge about optimal control to understand it. You can carefully follow the slides with your own pace and get to the end of it, and you just need to know what Lagrange multipliers are from your calculus course. So let's start. If I want to summarize it in one sentence, I would say MPC is a closed loop or real-time implementation of optimal control. You may say that you are pretty happy with the PID controllers you have used so far. Why not use a PID? The fact is that PIDs are usually used for linear systems or almost linear systems. And what I mean by that is a nonlinear system which operates in a limited region. You don't really see the effect of the nonlinearity of the system in that operating region. The other point is that PID is a single input, single output controller. So if you want to control a multi-input, multi-output system, you would need many PID controllers in different loops. And designing such a configuration is not easy. The other point is that tuning PID controllers is not an easy task, especially when you're dealing with a nonlinear system and there are state and input constraints. On the other hand, MPC can handle constraints on inputs and states for linear systems and nonlinear systems with multiple inputs and outputs. Therefore, you can replace a set of PID controllers with just one MPC controller and give it all the measurements that you have, and the MPC controller would compute all the inputs that you need to control the system. MPC is a systematic model-based approach, and what it means is that it's a tool to generate a control algorithm given the model of the nonlinear system and the objective of the control system. And in this webinar, we will talk about tools to generate the code for MPC controller automatically, so the user doesn't need to know how the constraints are handled, but the only thing that they need to know is how to change the design parameters to get to the desired behavior for the closed loop system. For example, consider a race driver. A race driver has to look forward in order to be able to react to the situation in a timely manner. And also, the driver wants to get to the finish line as fast as possible. However, there are limitations in this problem. So for example, it depends on the vehicle's dynamic behavior, what type of vehicle you're driving, or the limited power that you have access to. You don't want to skid too much so that the vehicle is not out of control. You have to follow the road, and you don't want a collision. These are constraints of this optimal control problem. At the beginning, MPC controllers were considered computationally expensive. So the first applications were in the chemical industry, where the time constant of your system is a few minutes, and that gives you enough time to run the MPC algorithm and compute the control inputs. Later, with faster hardware and better algorithms, we see applications of MPC everywhere, including in mechatronic systems such as different kinds of robots or washing machines. In the automotive industry, one example is engine controllers. In aerospace, it's used for aircraft control, spacecraft formation, and attitude control. It is also used in the power industry and more recently in computational biology. Consider a nonlinear dynamic system with x as the state vector and u as the input vector, and also an optimal control problem for this system where we want to minimize a cost function, which is a function of the final state plus the effect of the trajectory of the system going from the initial time to the final time. The constraints for this optimization problem are system's dynamic equations plus a set of equality constraints defined by GI as a function of states and inputs, and also a set of inequality constraints on states and inputs defined by HIs. Solving an optimization problem with inequality constraints is not easy because of the complexity of the optimality conditions known as KKT conditions. In this case, we use a particular interior point method known as the barrier method to convert the inequality constraints to equality constraints. For example, if HI has to be less than or equal to 0, we write this as HI plus alpha I squared equals to 0, where alpha I is a slack variable. If the problem is feasible, in the end, HI would be equal to minus alpha I squared, and for any given real value for alpha I, HI would be less than or equal to 0. We have also modified the cost function by adding the term minus R transpose alpha to the cost function, and that is to give incentive to the solver to stay away from the boundaries of the feasible set. So if the entries of R are small positive numbers, the hope is that the solution of this modified optimization problem is close to the solution of the original optimization problem with inequality constraints. Now, we discretize the problem into n time steps from T0 to Tf. The main things that change in the optimization problem are the cost for the final state, which is now defined as phi d, and also the system equations now written as difference equations. So phi d and fd are functions of delta tau, which is our time step. Now we can summarize the optimization problem as an optimization problem subject to only equality constraints, where we have put all the equality constraints into one vector called capital G. To solve an optimization problem subject to equality constraints, we use Lagrange multipliers. The way it works is to write the Lagrangian as the sum of the cost function, plus for each equality constraint, you would write the corresponding function multiplied by a Lagrange multiplier. In our case, we have called the Lagrange multipliers corresponding to systems dynamic equations as lambdas, and the rest of them are called nu. If the Lagrangian is differentiable with respect to all variables, any maximum or minimum of the optimization problem has to satisfy this optimality conditions. Basically, the derivative of Lagrangian with respect to all variables have to be 0. With slight manipulations, you can rewrite the Lagrangian as the form you see here, where capital H is known as the Hamiltonian of our optimization problem. If we call the optimal solution of x as x star and do the same thing for other variables, we can summarize the optimality conditions as the equations in this table. These are called Pontryagin maximum principle equations. The first two lines are the system's dynamic equations with its initial conditions. The next two lines are dynamic equations corresponding to the Lagrange multiplier lambda with its final conditions. So these equations have to be solved backward in time. And the rest of the equations are equality constraints on all the variables. That includes the partial derivative of the Hamiltonian with respect to u, and the partial derivative of the Hamiltonian with respect to alpha, which is the vector of slack variables, and also the original equality constraints that we had in the optimization problem, capital G equals to 0. What we saw so far was an optimal control problem. MPC is to solve an optimal control problem in each time step of a discrete time controller. The way it works is that while the system is working, we measure or estimate the current state. Then we solve an optimal control problem to compute the input for the next n steps. We return only the first step of this sequence, and that is the computed input, and that will be applied to the system. Then we'll repeat the loop again and again. Therefore, MPC is an implementation of an optimal controller in real time. Now, the question is how to solve optimality conditions in real time. The method that I will explain in this webinar is called Continuation GMRes method, or CGMRes method. It was proposed by Professor Otsuka in 2004, and it's been implemented by Cybernet Japan in Maple. You can find this implementation in Maple's Application Center on our website. The good news is that the implementation is done in a way that you can easily apply it to other examples. The method consists of two steps. In step 1, you solve the dynamic equations of the system forward in time, and then dynamic equations of the co-states, the lambdas, backward in time in order to compute all the states and co-states in terms of other variables. In the second step, we put all the remaining variables together in a vector called capital U. That includes the inputs, the slack variables, and the Lagrange multipliers nu for the time steps from 0 to n-1. And then we can write the remaining optimality conditions as a function capital F of the current state and capital U equals to 0. Now we should solve for capital U using the equation F equals to 0. The problem is that F is a nonlinear function, and this equation cannot be solved easily in general. This is how the optimality conditions are solved using the CGMRes method. The first part is the continuation method. Instead of solving F equals to 0, we find U such that F dot equals to ASF, where F dot is the derivative of F with respect to time, and AS is a constant matrix with negative eigenvalues. This is the design parameter. So if this equation is satisfied, regardless of where we start with F, it can be non-zero, it will converge to 0, because this is the dynamics of a stable linear system. Now, the derivative of F with respect to time can be computed using partial derivatives with respect to x and u. So we have fx x dot plus fu u dot equals to ASF. This equation has a very interesting property, and that is it's linear in u dot. Given the states, the current states, and the current value of capital U and the vector field of the system, we can compute everything except u dot. And this is a linear equation, so we just need to use a linear solver, in this case the generalized minimum residual or GMRes algorithm, to compute u dot. Once we have u dot, given the current value of u, we can update it and compute the new value of u and return the computed control signal. If all of this seems complicated, you can find more details in Professor Otsuka's paper. But if you're just a user who needs an MPC controller for an application, I have good news for you. All of the CGMRes method has been implemented in Maple. I will show you a Maple worksheet which comes with an MPC package. In that worksheet, you can enter the equations of your system, you can enter the constraints on inputs and states of that system, and when you run the worksheet, it will generate C code for an MPC controller using the CGM-res method, and it will simulate the closed loop system. In the worksheet that I will show you, you will see an MPC controller generated for controlling the position and orientation of a hovercraft. This is the model of the hovercraft. We will control position X and Y and orientation theta using the forces U1 and U2 generated by the thrusters of the hovercraft. This example is taken from a paper by Seguchi and Otsuka. You will see full information of the paper in the references slide. Dynamic equations of the hovercraft are shown here with the variables and their units. This is what we will enter into the worksheet to describe our system. You can find the example worksheet on our website. Just go to maplesoft.com, Resources, Application Center, and then search for Nonlinear Model Predictive Control, or NMPC, to get to this page. Here you can download a zip file containing the worksheet and the package, and also separately you can download a PDF document to explain what the worksheet does. What this worksheet contains is an implementation of the CGM-res method for MPC controllers, and it also contains automatic code generation. So here we will generate C code and compile it and run it to simulate the closed loop system. If you open the zip file, you will find a Maple worksheet called AutoGenU. The first section is Introduction, which contains the theory of the CGM-res method, so that you can go over the equations and definitions. You can also see some references here if you're interested to know more details. Let's close the introduction section. In the initialization section, I first press on this button to run the initialization code. Then we need to enter the current directory here, and we can check it using this button. So now that the two match, we can continue. Now we need to define our system, and we begin by defining the dimensions of the state vector, the input vector, the number of constraints, and the number of time varying parameters. In our case, we have 6 states for the hovercraft model that consists of x, y, theta, and their derivatives. In the inputs, we enter inputs and slack variables for inequalities, which are considered as virtual inputs. So we have 2 inputs for the system and 2 constraints for which we have slack variables. We add them together 4. Here the number of constraints are 2, and we have 0 time varying parameters. Now I press this button to create the vectors. So the dimensions are created, and the state vector, the co-state vector, the inputs and slack variables, and the Lagrange multipliers for constraints. And we don't have any time varying parameters in this system. Now we will define the vector field, the constraints, and the cost function. In the first box, you can define intermediate variables or temporary parameters if needed. Just don't forget to press Ctrl E on your keyboard to execute the code. Then the vector field is defined in FXU box. The constraints are defined in CXU box. And in our case, the vector of time varying parameters is empty. Now execute the code. The vector field is generated and the constraints. Here U1 and U2 are the inputs of the system. U3 and U4 are the slack variables, and Umax and Ubar are fixed parameters that will be defined later. The next step is to define the matrices in our case Q corresponding to the states, R for the inputs, and SF for the cost of the final state or the terminal penalty, which are the diagonals of these matrices. Now L is defined, the integrand of the cost function, and phi, the terminal penalty. Execute the code to generate the functions. So now the cost function is also defined. The next step is to introduce any fixed parameters. So in our case, for example, U max, U mean, U bar, and the other parameters of the system are defined here, like the mass of the hovercraft. And in case there are any arrays, we can define them here. The parameters of the cost function are defined here, and the final state that we want to go to. So I just execute the code. All of these parameters, scalar and vector, are defined. Now we define the simulation parameters, the initial time, the final time, the time step in simulation, the final horizon length, which is the prediction time of the MPC controller, the parameters of the MPC controller, the initial state, the initial input, the tolerance, and the step size in forward difference approximation of the partial derivatives. Number of iterations in the GMRes algorithm, number of grids in the horizon, and number of steps for saving data is here. You specify the file name for the C code and the header of the data files here. We now set the simulation parameters. There are some simplification algorithms that can be executed on the code. If you want, you can change these default settings, but for now I just go with the default settings. So I just execute to say that we don't want any simplification at this point. Now we check the dimensions of the parameters. It's approved. The name of the file that we want to save the data as an MPL file, we can set it here. I just press this button to save the data. Now for C code generation, we need to compute some derivatives. By pressing this button, you just define a procedure to compute the derivative of f with respect to x for different cases. Now using that procedure, we compute partial derivatives of the Hamiltonian. First we define the Hamiltonian, and then the vector of inputs, slack variables, and Lagrange multipliers for constraints, its dimension, and then we compute the partial derivatives of the Hamiltonian with respect to states and inputs, slack variables, and Lagrange multipliers corresponding to constraints here. If simplification is requested, they are simplified using the simplify command in Maple. Now we define the dynamic equations for the co-states. Again, if simplification is requested, it is executed. We compute the derivative of the terminal penalty with respect to the states. Now that we have defined everything, we can take advantage of the power of Maple in simplifying procedures. Here there are boxes for time-varying parameters, if any, partial derivative of the terminal penalty with respect to the states, the vector field of the system, the vector field corresponding to the co-states, and the partial derivative of the Hamiltonian with respect to inputs, slack variables, and Lagrange multipliers corresponding to constraints. So by checking each of these boxes, I'm asking for the optimized command of the CodeGen package to be executed on the corresponding procedures in this case. So I just execute the code to generate optimized straight line programs. The way it works is that it introduces some intermediate variables, and the final result will be calculated based on the input arguments and intermediate variables in order to reduce the number of operations. In this case, you see the straight line program that is optimized for computing the vector field of the system. And the last one is the straight line program for computing the partial derivative of the Hamiltonian with respect to u. At this point, we can generate C code for the MPC controller. There are a few options here regarding the sampling period, resetting u dot to 0, or using the Adams method. You can do experiments with these options to see which one improves the performance of your controller. I now run these commands to assign the name of the C functions that are generated, and by pressing this button you generate the code. In the next section, we can run the simulation by compiling the code. So you can set the compiler settings here to different types of compilers. One option is to use the one that comes with Visual C++, the other one is GCC, or you can use also a custom compiler. I press this button to compile the code and run the simulation. Now that we have the results, we can look at them as graphs in Maple. So just set the parameters where the data file is located, read the data file, and finally create graphs and show them. Here you can see graphs of states and inputs and slack variables and Lagrange multipliers in this simulation. This worksheet has been created by engineers at Cybernet company in Japan, and it's a very good example of using Maple to solve engineering problems. This is not just an example worksheet for the hovercraft example. It's a workflow that you can use to generate nonlinear MPC controllers for your own application. You just need to change the definitions of the vector fields and the design parameters of the controller and run the worksheet to get the code for the MPC controller and to run a closed loop simulation for your application. These are the main references that I used in this webinar in case you are interested to know more details about the CGMRes method. And this concludes our first webinar on MPC. Try the worksheet, let us know how it goes, and also let us know what kinds of applications you are interested in. That will help us in choosing the topics of the next webinars. Thank you.